Tonight, we're going to talk about the smallest star ever discovered in the universe. Stars come in a huge range of sizes. Massive blue giants on one end, small dim red dwarfs on the other. But there's a limit. A lower boundary, where a star simply can't hold on to the fusion that makes it a star at all. Somewhere out there, astronomers found an object sitting right at that limit, so close to the edge that a slightly smaller mass would have left it as something else entirely, cooling quietly in the dark instead of shining. By the end of tonight, you're going to understand exactly how astronomers found it, what makes it so extreme, and why it will keep burning for longer than almost anything else in the sky. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Most people, when they think of stars, picture something like our sun, a blazing sphere of white-yellow light. Something enormous, something luminous, something that powers an entire solar system just by existing. And that image isn't wrong. But it's deeply incomplete. The sun is, by the standards of the universe, a fairly average star. Not particularly large, not particularly small. Comfortably in the middle of a distribution that spans an enormous range of masses, sizes, and energies. And the universe has a tremendous amount happening on the smaller end of that scale that we almost never talk about. The stars that never make it into textbooks. The ones that sit in the darkness, burning so faintly that even at close distances they'd be essentially invisible to the naked eye. These are red dwarf stars, and they are, by a vast margin, the most common type of star in the Milky Way. Roughly 70 to 75% of all stars in our galaxy are red dwarfs. Not a slim majority, not even a commanding majority, a dominant, overwhelming majority. Every random star you would encounter in the galaxy has better than even odds of being a red dwarf. The bright stars we see at night, the ones that form the constellations, the ones that inspired centuries of mythology and helped sailors navigate open oceans, those are the rare exceptions. The red dwarfs are the rule. Smaller, cooler, and dimmer than the sun, every single one of them. Some dramatically smaller. And at the very bottom of that range, right at the edge of what physics allows, sits a star that pushes the definition of the word to its absolute limit. The story of the smallest known star begins with a question that sounds almost philosophical. What is the minimum amount of material you need to make a star? The answer depends entirely on physics. Specifically, on the mechanics of nuclear fusion and the pressure required to sustain it. A star is, at its core, a sustained thermonuclear reaction. Hydrogen nuclei are being forced together with enough pressure and temperature that they fuse into helium, releasing energy in the process. That energy pushes outward, opposing gravity's attempt to compress the whole structure inward. The two forces balance. The star holds its shape. That balance, fusion pushing out and gravity pulling in, is what defines a star. Without sufficient mass, gravity can't compress the core enough to reach fusion temperatures. The object just sits there, warm, dimly glowing from the heat of gravitational compression alone, but never actually fusing hydrogen into helium. That's what a brown dwarf is. A failed star. And something that almost made it, but didn't quite accumulate enough material to cross the line. The boundary between a brown dwarf and a true star sits at approximately 8% of the Sun's mass. Below that threshold, the core never reaches the roughly 10 million degrees Celsius needed to sustain hydrogen fusion. Above it, fusion ignites, the object stabilizes, and you have a star. That threshold is the floor, the absolute minimum. And the star we're talking about sits just barely above it. EBLM J0555-57 AB. That's the designation. Inelegant, certainly. But what it represents is extraordinary. It was discovered and characterized in 2017 by a team led by Alexander von Boeticher at the University of Cambridge. It was found not through direct imaging, but through a transit detection. The star passes in front of its much larger companion star from our line of sight, causing a tiny, periodic dip in that companion's brightness. By analyzing that dip in detail, its depth, its duration, its precise shape as a function of time, astronomers were able to calculate the smaller star's size and mass with remarkable precision. And what they found stunned them. Its radius is approximately 0.84 Jupiter radii. Jupiter is a planet. The largest planet in our solar system. Certainly, but still a planet. And this star is smaller than Jupiter. Its radius works out to roughly 37,000 miles. The Sun's radius is approximately 432,000 miles. That means this star is about 12 times smaller than the Sun in terms of radius. Its mass is approximately 85 times the mass of Jupiter, or about 8.5% of the Sun's mass. That puts it right at the edge, barely above the hydrogen fusing threshold. If you stripped away a small fraction of its mass, it would cross the line into failed star territory. It wouldn't be a star anymore. To understand why this matters, you need to understand what's happening inside a star of this size. In our Sun, fusion occurs throughout a large core region. The temperatures and pressures at the center reach about 15 million degrees Celsius and around 250 billion times Earth's surface atmospheric pressure. That extreme environment drives fusion at an enormous rate. The Sun converts roughly 600 million metric tons of hydrogen into helium every single second. Every single second. It has been doing this for 4.5 billion years. It has enough fuel left to continue for roughly another 5.5 billion. That's what fusion at solar scales looks like. In EBLM J0555-57 AB, the internal conditions are barely sufficient. The core temperature hovers near the minimum needed to sustain proton-proton chain fusion. The pressure, while enormous by any terrestrial standard, is at the low end of what stellar physics requires. The fusion reaction proceeds, but slowly, hesitantly, in a sense. The star produces a tiny fraction of the energy per unit volume compared to the Sun. Its luminosity, the total energy it radiates, is estimated to be somewhere around 2 to 3 thousandths of the Sun's total output. You could stack hundreds of these stars together and still not match the Sun's brightness. Standing near this star, at the same distance as Earth is from the Sun, the sky above you would not look like a daytime sky. It would look more like deep twilight. A dim, reddish glow in one direction, stars still visible overhead, the landscape illuminated just enough to cast faint shadows. This star gives off light, but barely. And most of that light falls outside the wavelengths the human eye can use. The color of that light matters in ways beyond just aesthetics. EBLM J0555-57 AB, like all red dwarfs, radiates predominantly in the red and infrared portions of the electromagnetic spectrum. Stars produce light based on their surface temperature. Hotter stars glow blue and white. Cooler stars glow orange and red. The Sun's surface sits at around 5,500 degrees Celsius, about 9,900 degrees Fahrenheit, producing that characteristic yellowish-white light. Its surface temperature is estimated at somewhere between 2,700 and 3,000 degrees Celsius, roughly 4,900 to 5,400 degrees Fahrenheit. By comparison, a candle flame reaches about 1,400 degrees Celsius, roughly 2,550 degrees Fahrenheit. This star's surface is roughly twice as hot as a candle. In any other context, twice as hot as a candle would sound intensely hot. In the context of stars, it's the coolest possible while still being a star. The light it produces peaks deep in the red, with most of its energy output actually in the near-infrared, wavelengths just beyond what the human eye can detect. If you were standing near this star and looking at it, you would see a deep, saturated red disk in the sky, darker and more intense in color than any sunset you've ever seen. Most of what it's radiating, you simply wouldn't be able to see at all. Your skin would register warmth before your eyes registered meaningful light. The star would be there, real and burning, and the experience of standing under it would feel like a mild, overcast afternoon under strange red light. Not a blazing midday, something quieter and dimmer and stranger than anything our planetary experience has prepared us for. When EBLM J0555-57 AB was announced in 2017, it broke a record. At the time of its detailed characterization, it was identified as the smallest known star with confirmed hydrogen fusion. The system it belongs to is located roughly 600 light-years from Earth, in the general direction of the constellation Pictor. It orbits a much larger companion star, the primary in the system, in a tight orbit. The period of that orbit is about 7.8 days, meaning it completes one full circuit around its companion in just under 8 days. Mercury, the innermost planet in our solar system, takes 88 days to orbit the Sun. This tiny star laps its companion in a fraction of that time. The name itself reflects the kind of observational program that finds these objects. EBLM stands for Eclipsing Binary Low Mass, a category of stellar system specifically designed to detect and study small, cool stars in binary pairs. The transit method that revealed this star is the same basic technique used by planet-hunting missions like the Kepler Space Telescope and the Transiting Exoplanet Survey satellite. When a smaller object passes between us and a brighter background source, it blocks a small fraction of the light. The amount of light blocked tells you the size ratio of the two objects. Combined with spectroscopic measurements that reveal the companion's mass and the orbital dynamics of the system, you can reconstruct the smaller object's properties in detail. For EBLM J0555-57 AB, this analysis revealed something at the very boundary of stellar existence. The team at Cambridge wasn't primarily searching for a record-breaking star. They were conducting a systematic survey, part of the WASP project, the Wide-Angle Search for Planets. WASP was originally designed to find planets transiting nearby stars using a network of wide-field cameras to monitor the brightness of hundreds of thousands of stars simultaneously. The system flags anything that shows a regular, periodic dimming. Most of the time, the culprit is a planet. But Occasionally, it's a small companion star, EBLM J0555-57. AB was flagged as one of those rare small star detections. When the team followed up with spectroscopy from instruments at the European Southern Observatory, they were able to pin down the masses and radii with enough precision to understand what they had found. Alexander von Boeticher described it as being about as small as a star can possibly be. That phrase is not hyperbole. It reflects a genuine physical boundary. Below a certain size and mass, the object can't sustain fusion, and it's no longer a star by any definition that matters physically. It sits just on the right side of that boundary, just barely. To really understand what that size means, it helps to think carefully about what Jupiter actually is. Jupiter has a mass about 318 times Earth's mass. It's massive enough that all the other planets in the solar system combined would fit inside it with room to spare. Its diameter is about 11 times Earth's. It has dozens of known moons, a magnetic field far stronger than Earth's, its own internal heat from slow gravitational contraction, and complex atmospheric dynamics, including storms that persist for centuries. By any measure relevant to planetary science, Jupiter is extraordinary. And EBLM J0555-57 AB is smaller than it. A star. Smaller than a planet in our own solar system. This isn't a measurement error. This isn't an artifact of how the numbers are scaled. This is what physics allows at the minimum stellar mass. The electron degeneracy pressure that resists further compression in very low mass objects means that adding more mass beyond a certain point doesn't proportionally increase the size. Below a certain mass, objects in this regime, whether giant planets, brown dwarfs, or the smallest stars, all cluster around a similar radius. The smallest red dwarf stars and the largest gas giant planets overlap in physical size. What separates them is not their radius. It's what's happening inside. It's whether the core is fusing hydrogen. That's the entire distinction between a planet and a star at these scales. Not size. Not color, at least not definitively. What's happening in the core? There's something quietly strange about that when you sit with it. We tend to think of stars and planets as belonging to fundamentally different categories. Stars are enormous. Planets are smaller. Stars burn. Planets don't. That intuition comes from our solar system, where there's a large, obvious gap. The Sun is enormously bigger than even Jupiter. The categories feel natural and obvious. But out in the broader universe, that gap doesn't always exist. The smallest stars are planet-sized objects. The largest planets approach the sizes of small stars. Nature doesn't always respect the categories we find convenient. And at the boundary, the only thing that matters is the nuclear physics happening in the core. 8% of the Sun's mass, and you have a star. 7%, a failed star. The universe makes that distinction. Not based on size, not based on what it looks like from the outside, based entirely on what's happening in the interior. The same object, with slightly different mass, is either a star with a potentially multi-trillion-year future or a slowly cooling object moving toward darkness, depending entirely on whether it crossed that threshold. Let's step back and look at the broader landscape of small stars, because EBLM J0 555-57. AB doesn't exist in isolation. It's the most extreme known example of a phenomenon that is, statistically speaking, the dominant form of stellar life in the universe. Red dwarf stars, classified as M-type stars on the standard stellar classification scheme, span a range from about 40% of the Sun's mass down to that minimum near 8%. That range is large enough that red dwarfs come in dramatically different varieties. A red dwarf at 40% of the Sun's mass is still a fairly substantial object. It might have a radius around 40% of the Sun's. Its luminosity might be a few percent of the Sun's. You could detect it from hundreds of light years away with modest equipment. But as you move down the mass scale, things change rapidly. Luminosity drops faster than mass. Far faster. Halve the mass and the luminosity doesn't just halve. It falls by a much larger factor. The relationship between stellar mass and luminosity follows a steep power law for low-mass stars. Small changes in mass produce very large changes in brightness. This means that the faintest, smallest red dwarfs are dramatically harder to detect than their slightly larger cousins. They hide in the dark. They don't announce themselves with visible light. They need careful, targeted observations in the infrared to reveal themselves. And because of this, for most of human astronomical history, we didn't know how common they were. The count, when infrared surveys finally started providing it, was surprising. Shocking, actually. The galaxy is absolutely dominated by stars that are, for all practical purposes, invisible to the unaided human eye. Every single one of the nearest stellar systems to our solar system, the ones close enough that we know their properties in reasonable detail, includes red dwarfs. Proxima Centauri, our nearest stellar neighbor at 4.24 light-years, is a red dwarf. Barnard's star, the second closest individual star to the Sun, is a red dwarf. Wolf 359 is a red dwarf. Lalande 21185 is a red dwarf. UV Ceti is a red dwarf system. The Sun, in terms of the local stellar neighborhood, is the oddity, the large, bright, energetic exception to a rule that says most stars are small and dim. If you didn't have the special advantage of living next to a sun-like star and instead orbited an average star in the galaxy, you'd be orbiting a red dwarf. That's the baseline. That's what normal looks like in the Milky Way. And we've spent most of our history studying the exception. There's something almost unsettling about this when you really internalize it. We built our entire intuition about stars around the Sun. Our sense of what a star looks like, how bright it is, how long it lives, what it does to its surrounding space. All of it comes from one particular star that happens to be our local example. But the Sun is, in terms of stellar demographics, a statistical outlier. Not dramatically so. It's not a massive blue giant or a red hypergiant, but it's in the upper half of the mass and luminosity distribution. It's brighter and more massive than the majority of stars that exist. The median star in the Milky Way is something closer to half the Sun's mass. Something dim and red, burning much more slowly, living for a time span that makes the Sun's 10 billion-year life look brief. And the smallest known star, EBLM J0555-57, AB, is nowhere near even that median. It's at the floor. As far from our Sun in stellar terms as you can get while still qualifying as a star at all. If you were to randomly select any star from the Milky Way and look at it, there's better than a 70% chance it would be smaller, dimmer, cooler, and redder than the Sun. We learned what stars look like from one of the unusual ones. This discovery matters not just as a record. It matters because the physics of stars at this size is genuinely different from the physics of larger ones in ways that affect some of the biggest questions in astronomy. Questions about habitability. Questions about the future of the universe. Questions about where life might exist and for how long. The most striking difference is longevity. Stars consume hydrogen fuel to produce energy. The rate at which they consume it depends on their luminosity. More luminous stars burn faster, less luminous stars burn slower. The Sun will remain on the main sequence, stably burning hydrogen for roughly 10 billion years total. It's currently about 4.5 billion years in. That leaves another 5.5 billion years of relatively stable burning. A long time. An almost incomprehensible span by any human measure. But from the universe's perspective, the Sun is burning hot and fast. The smallest red dwarfs will outlive the Sun by factors that strain language. A star with 8% of the Sun's mass, sitting right at the minimum threshold, burns its fuel so slowly that models predict it can sustain fusion for somewhere between 100 billion and several trillion years. The universe is currently about 13.8 billion years old. The Sun has been around for less than a third of that. But a star at the minimum mass could still be burning long after the Sun has swollen into a red giant, shed its outer layers, and collapsed into a cold white dwarf. Not just somewhat longer, not twice as long, or 10 times as long. Many times longer than the current age of the universe. On a timescale that makes the Sun's entire life look like an opening chapter in a very long book. This has implications that extend far beyond the eventual fate of our solar system. At some point in the far future, the universe will reach a state where all the massive stars are gone. They live fast, burn brilliantly, and expire quickly on astronomical timescales. Blue and white stars exhaust their fuel in millions to tens of millions of years. Sun-like stars last billions of years, but eventually exhaust their core hydrogen too. The white dwarfs they leave behind cool slowly toward darkness over trillions of years. And in the far future, in epochs so distant that the language we have struggles to carry the numbers, the only stars still actively fusing hydrogen will be the red dwarfs. The universe will belong to the smallest stars, the ones we can barely see now. EBLM J0555-57. AB and its cousins will outlive every other type of star. Every blue supergiant, every Sun-like G-type star, every type of star associated with the familiar starlight of the night sky will be gone, converted into remnants. White dwarfs, neutron stars, and black holes will be what remains of the earlier stellar generations. And in the darkness, after all of that, the red dwarfs will still be there, burning slowly, patiently, in a universe otherwise cold and growing colder. Eventually, even they run out. When the last red dwarf finally exhausts its hydrogen, it too becomes a white dwarf, slowly cooling toward darkness, eventually becoming a black dwarf, an object so cool it emits essentially no radiation. Though no black dwarf has ever been observed, because the universe hasn't been around long enough for any star to complete that final journey. EBLM J0555 5-57 AB, barely begun in cosmic time, has almost its entire future still ahead. The relationship between small stars and potential life is one of the most active debates in modern astrobiology. Reasonable scientists land on opposite sides of it, which means the evidence isn't yet decisive enough to close the question. On one hand, the longevity is extraordinary. If life needs time, if the emergence of complex biology requires billions of years of stable conditions, then the planets orbiting red dwarfs have that in abundance. More than any other class of star. Our sun changes meaningfully over billions of years. It was somewhat dimmer in the early solar system than it is today, and it will brighten further as it ages. Those changes matter for climate, for habitability, for the long-term survival of a biosphere. The smallest red dwarfs change so slowly, over such vast timescales, that for most practical purposes, the energy they provide to their planets is effectively constant on any timescale that biology operates over. A planet orbiting EBLM J0555-57 AB sits in a thermal environment that barely shifts over spans of time longer than Earth's current age. Billions of years of stability. That could be a tremendous advantage for life. Stability for chemistry to complexify. Stability for organisms to evolve. Stability for ecosystems to develop and complexify over timescales that dwarf what evolution has had access to on Earth. But small red dwarfs come with serious complications. The same properties that make them long-lived also make them potentially hostile in other ways. Red dwarf stars, especially the smallest ones, are magnetically active, very active. More active, in certain respects, than the Sun. A large solar flare on the Sun might briefly increase its output by a small fraction of its total luminosity. A major flare on a small red dwarf can temporarily double or triple its luminosity. These flares release bursts of ultraviolet radiation and high-energy particles. For a planet in the habitable zone of a small red dwarf, these events aren't minor inconveniences. They're bombardments. Repeated, intense, energetic bombardments of radiation that could strip atmospheric gas away over geological timescales and damage or destroy complex organic molecules at the surface. The smallest red dwarfs are among the most prolific flarers. Stars like EBLM J0555-57 AB may be particularly aggressive in this regard, especially in their early lives when stellar magnetic activity tends to be most intense. Whether any planet orbiting such a star could maintain conditions favorable to life remains genuinely uncertain. The uncertainty runs in both directions. We can construct models where life survives and even thrives. We can construct models where the radiation environment makes the emergence of biology essentially impossible. We don't yet have the observations to know which models are right. The only way to find out is to look at actual planets orbiting actual red dwarfs, which is exactly what the current generation of observatories is trying to do. There's another complication that comes with orbiting a small red dwarf, and it fundamentally shapes what any life there would experience. The habitable zone around a small red dwarf, the region where liquid water could theoretically exist on a planet's surface, is very close in, much closer than Earth's orbit around the Sun. The smaller and cooler the star, the more tightly wrapped the habitable zone is around it. For a star like EBLM J0555-57 AB, which emits only a tiny fraction of the Sun's energy, a planet would need to orbit extremely close to receive enough warmth for liquid water. We're talking about orbital distances far shorter than Mercury's distance from the Sun. At these close distances, a process called tidal locking becomes essentially inevitable over geological time. Gravity is not perfectly uniform across a nearby extended object. The side of a planet facing a nearby massive star experiences a stronger gravitational pull than the far side. This difference in gravitational pull across the planet's diameter creates a torque that gradually slows the planet's rotation. Over millions to billions of years, the rotation period lengthens until it exactly matches the orbital period. At that point, one hemisphere permanently faces the star. The other is in perpetual darkness. The star never rises on the night side. The star never sets on the day side. One hemisphere bakes in endless daylight under the permanent red glow. The other freezes in endless night. Extreme temperature differentials between hemispheres would drive powerful atmospheric circulation, heat flowing constantly from the lit side toward the dark, creating permanent wind patterns unlike anything on Earth. Whether liquid water could persist at the terminator, the ring between day and permanent night, where temperatures might be moderate, remains uncertain. But the universe has had more than 13 billion years to run this experiment on billions of worlds around billions of red dwarf stars. The outcome of that experiment is one of the defining open questions in modern science. And the smallest stars, like EBLM J055 5-57AB, represent the most extreme version of those conditions. One aspect of small stars that deserves careful attention is what happens in their earliest years. The pre-main sequence phase for the smallest red dwarfs is not brief. For Sun-like stars, the pre-main sequence phase, the period before the star settles into stable hydrogen burning on the main sequence, lasts tens of millions of years. For the smallest red dwarfs, this phase can last much longer. Billions of years in some cases, depending on the mass. During this extended pre-main sequence period, the star is often more luminous than it will eventually become on the main sequence. It's also more magnetically active, more prone to flaring. A planet that will eventually sit in what becomes the habitable zone. Once the star dims down to its long-term steady-state luminosity, spends those early billions of years exposed to intense radiation from a star that's brighter and more violent than the one it will ultimately orbit. By the time conditions improve and the planet finds itself in a more temperate zone, the surface may have been repeatedly battered. The atmosphere may have been partially or entirely stripped by stellar winds and radiation pressure. Water may have been photodissociated by ultraviolet radiation and lost to space over time. The planet may arrive in the habitable zone in a depleted state, with whatever volatile inventory it started with substantially reduced. This doesn't make life impossible. Life might arise in shielded environments, underground or in deep water, and eventually colonize the surface when conditions improve. Or the planet may retain enough atmosphere and water despite the early bombardment to remain habitable. These are open questions. But the early phase is a hurdle, a serious one, and it's particularly acute for the smallest stars, where the pre-main sequence phase lasts longest and the habitability window is delayed by billions of years. Stars this small are also genuinely hard to find, and that difficulty matters for our census of the galaxy. EBLM J055 5-57 AB was identified because it happened to transit in front of its companion star from our line of sight. That geometry is a coincidence of position. For every binary system, where we happen to see transits, there are many more where the orbital geometry doesn't place the smaller star in our line of sight. The orbit exists. The star exists. But the transit never crosses our view. We never know the companion is there. Beyond binary systems, isolated red dwarfs at the extreme low end of the mass range are even harder to detect. They don't produce enough visible light to register on traditional optical surveys. You need targeted infrared observations. You need either to be looking in exactly the right place or to conduct a systematic all-sky survey in the infrared. Modern survey missions have dramatically improved our ability to find them, but the census is still incomplete. We know these stars are common. We know the smallest ones exist in large numbers. But precisely how many there are, how they're distributed throughout the galaxy, and how many host planetary systems remains an active area of research. Every new generation of instruments makes the picture sharper. The James Webb Space Telescope, with its extraordinary infrared sensitivity, is already contributing in ways that weren't possible before it launched. Its ability to characterize the atmospheres of planets orbiting nearby red dwarfs is unprecedented. It does this through transmission spectroscopy. As a planet passes in front of its star, some of the starlight filters through the planet's atmosphere before reaching our detectors. Different molecules absorb different wavelengths of light. By measuring which wavelengths are missing, astronomers can identify which molecules are present in the atmosphere. Water vapor, carbon dioxide, methane, oxygen, ozone. These all have distinct spectral signatures. This technique has already been applied to planets in the TRAPPIST-1 system. The results are being actively analyzed and debated. The field is young, and the data are still accumulating. But the capability is real and operating. Systems like TRAPPIST-1, a red dwarf hosting 7 known planets, with at least 3 of them in or near the habitable zone, are being scrutinized in a level of detail that was simply impossible a decade ago. TRAPPIST-1 sits at about 9% of the Sun's mass, slightly above the absolute minimum threshold. It illustrates the kind of compact, multi-planet system that forms around tiny stars. Close orbits. Multiple planets, packed in tight around a dim red source. It's become, arguably, the most scrutinized planetary system in the history of astronomy. Precisely because the star is small enough that its habitable zone planets are accessible to current instruments. What we're learning from TRAPPIST-1 applies directly to understanding what the environments of planets around stars, like EBLM J0555-57 AB might be like. Upcoming instruments are pushing the capabilities further. Extremely large ground-based telescopes currently under construction, including the extremely large telescope in Chile, with its 39-meter primary mirror, will provide light-gathering power and angular resolution that make current facilities look limited by comparison. These next-generation instruments will study individual red dwarfs in nearby systems with unprecedented detail. They will detect planets around them, probe their magnetic fields, measure flaring events, and characterize stellar surfaces with precision not currently achievable. The smallest stars, once nearly invisible to us, are becoming the focal point of some of the most ambitious observational programs in the history of astronomy. The reason for that focus goes back to those numbers about prevalence. If 70% of all stars are red dwarfs, and if even a modest fraction of them host worlds where the conditions for chemistry and biology persist over long timescales. The implications are enormous. There are somewhere around 100 billion stars in the Milky Way. If 70 billion of them are red dwarfs, and if even a small fraction of those have planets in stable, habitable zones, the galaxy may be far more biologically active than our sun-centric assumptions suggested. Full of chemistry around stars we've historically overlooked as too dim and too faint to be worth studying carefully. This is one of the most significant shifts happening in astrobiology right now. The assumption used to be that sun-like stars were the most promising hosts for life. We assumed life needed sun-like conditions because the only confirmed example, Earth, orbits a sun-like star. But that reasoning is circular. We're here, around this star, because we're here. That tells us life can emerge around sun-like stars. It tells us nothing definitive about everywhere else. The smallest red dwarfs offer conditions that are genuinely different. More intense radiation early on. Tidal locking. A compressed, habitable zone. But also enormous stability over time and sheer statistical abundance. There are far more red dwarfs than sun-like stars. If biology can find a way to get started in those conditions, it has had an enormous number of chances in the history of the universe. One of the more subtle but important points about EBLM J0555-57 AB's discovery is what it confirmed about stellar modeling. For decades, astronomers have been building increasingly sophisticated computer models of stellar interiors. These models take as input a star's mass and chemical composition, and they predict everything else: the internal temperature and pressure profile, the fusion rate, the luminosity, the surface temperature, the radius. The predictions from these models have long suggested that there's a minimum radius below which a main sequence star cannot go. The physics of electron degeneracy, a quantum mechanical effect that stiffens matter against compression, means that below a certain mass, adding more material doesn't proportionally increase the size. The star gets more massive, but not proportionally larger. This creates a turnover in the mass-radius relationship. In the brown dwarf regime, radii become relatively constant across a wide range of masses, all hovering near Jupiter's radius. EBLMJ 055-5-57a b, with its Jupiter-comparable radius, sits in exactly this zone, as small as a star can get, without crossing into the size range shared by giant planets. The models said this was where the boundary should be. The observation confirmed it. That kind of agreement between independent theoretical prediction and direct measurement is what gives scientists confidence that they're actually understanding the physics correctly. The internal structure of the smallest stars differs from the Sun in fundamental ways that shape their behavior and their longevity. The Sun is not convective throughout its entire volume. Its core, where fusion happens, is a radiative zone. Energy moves outward through the slow diffusion of photons, a journey that in the Sun takes somewhere between 10,000 and 100,000 years. A photon generated in the solar core doesn't stream outward in 8 minutes like sunlight does from the surface. It takes an enormously circuitous path through countless absorptions and re-emissions, bouncing around in a dense plasma for tens of thousands of years before reaching the outer convective layers. Above this radiative zone, the Sun's outer layers are convective. Hot material rises, cools, falls back, creating large circulation cells, driven by the temperature gradient. This creates the granular surface pattern visible in high-resolution solar images. This division between radiative interior and convective exterior has consequences for how the Sun generates its magnetic field and how material mixes through its interior. In the smallest red dwarfs, the situation is fundamentally different. Stars below, about a third of the Sun's mass, are fully convective. There is no radiative zone. Material circulates through the entire star, from core to surface and back again. This changes the magnetic behavior significantly. The dynamo that generates magnetic fields in stars operates differently in fully convective stars. In the Sun, the boundary between the radiative and convective zones plays a crucial role in the dynamo mechanism, organizing and amplifying magnetic field lines in a structured way. In a fully convective star, that boundary doesn't exist. The dynamo operates throughout the whole volume. The resulting magnetic field behavior is different. The Sun's 11-year sunspot cycle depends on the organized winding and unwinding of magnetic field lines at that boundary. Without it, fully convective red dwarfs generate their fields differently. Some show no regular cycle at all. Others show continuous, irregular magnetic activity. The flaring behavior that concerns astrobiologists is tied to this different magnetic architecture. EBLM-J 055 5-57 AB is fully convective throughout its entire volume. And this full convective mixing is part of what allows the smallest stars to live so long. They process their hydrogen more efficiently than partially radiative stars. In a Sun-like star, a significant fraction of the total hydrogen sits in layers that never participate in core burning and therefore never gets fused. For fully convective stars, the circulation mixes material throughout, allowing the star to burn a larger fraction of its total hydrogen inventory before running out. The efficiency is higher. The lifespan is longer as a result. The same full convection that creates the intense flaring may also be part of what gives these stars their extraordinary longevity. The features that make them potentially hostile and the features that make them enduring are connected. Stars are characterized by astronomers using a classification system that dates back more than a century, refined and extended over generations as instruments improved. The modern classification runs from O through B, A, F, G, K, and M, from hottest to coolest, from most massive to least massive. The Sun is a G-type star. The M-type stars are the red dwarfs. EBLM J 055 5-57 AB sits at the extreme cool end of the M-dwarf range. Below M dwarfs on the temperature scale, there are additional spectral types that have been added more recently as instruments became capable of detecting objects that weren't previously classifiable at all. The L dwarfs are cooler than the coolest M dwarfs. Then come T dwarfs and Y dwarfs, progressively cooler brown dwarf classes. The coolest known Y dwarfs have surface temperatures comparable to a warm oven, a few hundred degrees Celsius. They're brown dwarfs, slowly cooling, not stars at all. This star, with its surface temperature around 2,700 to 3,000 degrees Celsius, roughly 4,900 to 5,400 degrees Fahrenheit, sits right at the M dwarf to L dwarf boundary on the temperature scale. Late M type, right at the end of the stellar classification. The next step down in surface temperature, just a few hundred degrees cooler, and the object would no longer qualify as a proper M dwarf star. It sits at the end of the stellar alphabet. The story of how we got to the point of being able to characterize a star this small is itself a chronicle of improving technology and method spanning more than a century. In the early days of stellar astronomy, classifying stars at all was an extraordinary achievement. Annie Jump Cannon and her colleagues at the Harvard College Observatory in the early 20th century manually classified hundreds of thousands of stellar spectra. Their work produced the classification sequence still in use today. The M class was known to include some very faint, very small objects. But detecting and characterizing the faintest M-type stars was beyond the capability of early spectroscopy. The instruments weren't sensitive enough. The detectors weren't available. The sky surveys hadn't been conducted. The breakthrough came with infrared detectors. In the 1970s and 80s, as infrared array detectors began to emerge from military and industrial research programs into scientific use, astronomers could suddenly detect stars that had been essentially invisible. Surveys, like the 2-micron all-sky survey, conducted in the late 1990s and early 2000s, catalogued hundreds of millions of objects in the infrared for the first time. The Sloan Digital Sky Survey added optical coverage for enormous numbers of faint objects. Eventually, space-based infrared telescopes and dedicated transit survey programs like WASP made it possible not just to detect the smallest stars, but to measure them precisely, to pin down their radii and masses from orbital geometry rather than stellar model assumptions. We've come a long way from photographic plates and glass slides inspected under magnifying lenses. From manually cataloging stars one spectrum at a time, to automated pipelines processing millions of light curves simultaneously, flagging anything interesting for human follow-up. The methods transformed entirely. The question remained the same. What is out there? And how small can a star be? There are stars, just slightly larger than EBLM J0 55 5-57a b, that have been studied in detail and help fill in the picture of what stellar life at the extreme small end looks like. Proxima Centauri, our nearest stellar neighbor, has a mass of about 12.5% of the Sun's. It's larger than our record holder, but still tiny by stellar standards. Its radius is about 14.5% of the Sun's. Its luminosity is about 1/600th of the Sun's. Proxima is a flare star, well known for producing powerful ultraviolet bursts. It has at least one confirmed planet, Proxima b, in or near the habitable zone. Whether that planet retains an atmosphere, whether liquid water could exist there, whether the flaring activity over billions of years permits biology, these are being actively investigated. Proxima is close enough at 4.24 light-years that it offers a level of study not possible for more distant systems. What we learn from Proxima feeds into our understanding of stars like EBLM J0 55 5-57 AB. The same physical principles apply. Barnard's star sits at about 15% of the Sun's mass. Wolf 3, 5, 9, about 9%. These nearby examples give astronomers a sample of low-mass stars to study at close range, in ways that the more distant star cannot be studied. The local red dwarfs are the test cases that validate our understanding of what happens at the small end of the stellar mass scale. What works for nearby stars gets extended to more distant ones. And EBLM J055 5-57 AB sits at the extreme end of that continuum, where the properties become most pronounced and most interesting. The proximity of the smallest stars to the brown dwarf boundary has led to some genuinely interesting astrophysics around the classification question. Objects in the range of 70 to 80 Jupiter masses within a few percent of the hydrogen fusion threshold can be difficult to classify from observations alone. Their fusion rates are so low, their surface temperatures so similar to the top of the brown dwarf range, that distinguishing them requires careful measurement. Lithium is one of the most useful diagnostic tools available. Stars above the hydrogen fusion threshold destroy their lithium over time through nuclear reactions in the hot core. Specifically, lithium undergoes proton capture reactions at temperatures above about 2.5 million degrees Celsius. In the cores of genuine stars, where temperatures exceed 10 million degrees Celsius, this destruction happens relatively quickly on stellar timescales. Brown dwarfs, because their cores don't get hot enough for this destruction, retain their lithium over time. The presence or absence of lithium absorption in a candidate object's spectrum can help determine which side of the boundary it's on. This technique, called the lithium test, was developed in the 1990s and has been used extensively to confirm the nature of borderline objects. EBLM J0555-57. AB sits clearly on the stellar side. Its core has been hot enough to process its lithium. The test would confirm it's a genuine star. Some objects near the boundary show partial lithium depletion, suggesting conditions in the transitional zone where fusion is marginal and intermittent. This star is not in that transitional zone. It's a star, just barely, but genuinely. There's a broader point here about scientific categories that's worth making explicit. We draw lines. We say, this is a star, that's a planet. This other thing is a brown dwarf. Those categories are useful. They organize our understanding and let us talk about objects with shared properties as groups. But nature doesn't know about our categories. Nature produces a continuous distribution of masses. From gas giant planets through brown dwarfs, through the smallest stars, through the largest stars. No gaps in the distribution. No natural breaks where one type ends and another cleanly begins. Just a smooth continuum of masses. Our categories are imposed on that continuum by us, drawn at physically meaningful thresholds where genuinely different behaviors emerge. The fusion threshold is one such line. It's physically meaningful. There's genuinely different behavior on either side. An object fusing hydrogen is doing something qualitatively different from one that isn't. But the line is a threshold in a continuous process, not a gap in nature. The object at 79 Jupiter masses and the one at 81 Jupiter masses differ by 2 Jupiter masses. One is a brown dwarf. One is a star. The physics that distinguishes them is real. But from the outside, looking at their observable properties, they appear remarkably similar. This is a useful reminder that our categories describe nature. They don't constrain it. Nature doesn't arrange itself into tidy boxes for our convenience. It produces a continuum, and we find the meaningful boundaries within it. Let's think about what it would actually be like to stand near EBLM J0555-57 AB. The habitable zone around a star this faint sits at an orbital distance far inside where Mercury sits relative to the Sun. To receive enough energy for liquid water at the surface, a planet would need to orbit very close. Close enough that tidal locking would be essentially guaranteed on geological timescales. So, imagine standing on such a world. The star sits motionless in the sky. It doesn't rise or set. It hangs there, a deep red disk in one direction, unchanged day to day for as long as you live. From where you stand, near the terminator, on the side facing the star, the light is dim and reddish. Stars are visible even during what passes for daytime on this world, because the star's glow isn't bright enough to wash them out completely in a sky that only scatters dim red light. The sky is a dark, reddish purple. The stars overhead are clear, even while the star itself glows at the horizon. Toward the night side, the stars become fully visible without competition. The wind blows consistently from the day side toward the night side, carrying heat into the eternal dark. On the night side, without any starlight whatsoever, temperatures plunge. The ground freezes. Volatile compounds solidify. An environment that almost nothing on Earth has prepared you to understand. On the day side, under the direct, if dim glow of the star, temperatures are moderate if you're in the right zone. But periodically, without warning, the star brightens. A flare erupts. The ultraviolet output spikes dramatically for minutes or hours. If you're on the surface, you need shelter from the radiation. The environment during a flare is not gentle. What biology looks like in this environment, we don't know. What adaptations life would need to survive, we can only speculate from first principles. But the universe has created this environment around billions of red dwarfs, and it has had an enormous amount of time to run the experiment. It's also worth thinking carefully about the longer future of EBLM J0555-57 AB itself. The star is burning slowly, very slowly. The rate of hydrogen consumption is a tiny fraction of what the sun burns per second. Its total hydrogen inventory, 8.5% of the sun's mass, is smaller than the sun's. But it burns so much more slowly that the net result is a lifespan dramatically longer. The sun will exhaust its core hydrogen in about 5.5 billion more years, then begin its red giant phase. EBLM J0555-57 AB will continue burning hydrogen for something approaching 1 trillion years or more, depending on the precise mass and composition. During that time, the star will slowly evolve. As hydrogen is converted to helium in the core, the composition changes gradually. The core becomes richer in helium. The fusion rate adjusts to compensate. The star very slowly brightens over geological timescales. This brightening is much more gradual than what the sun experiences over comparable periods, and it unfolds over enormously longer timescales. A planet in the habitable zone around EBLM J0555-57 AB today will receive slightly more energy in 1 billion years than it does now. The habitable zone migrates outward very slowly as the star brightens over these vast spans of time. Eventually, after an enormous span, the star's core hydrogen is exhausted. What happens next for the smallest red dwarfs is something no star has yet demonstrated, because none has had time. Models suggest that the smallest red dwarfs may not become red giants the way the sun will. They may instead gently fade, their hydrogen depleted over their extraordinarily long lifetimes, contracting slowly into white dwarfs without the dramatic expansion phase. The ending, when it finally comes, may be as quiet as the life. No swelling into a giant. No shedding of outer layers as a planetary nebula. Just a slow fading, and then a white dwarf, slowly cooling over trillions of years. The question of whether EBLMJ 0555-57 AB has any planets is genuinely open. The system is actually a triple. Two sun-like stars form the outer pair, and the small star orbits one of them in a tight inner orbit. Planetary formation in systems like this is complicated. The gravitational influence of the companion can disrupt the protoplanetary disk around the smaller star, potentially preventing planet formation or destabilizing forming planets. Whether stable planetary orbits can exist close enough to EBLMJ 0555-57 AB to be in the habitable zone, given the gravitational influence of the larger companion, depends on the geometry of the system. Binary systems can host planets in a few different configurations. Planets can orbit one of the two stars closely, staying well within that star's gravitational sphere of influence. Or planets can orbit both stars together in large circumbinary orbits outside the influence of the inner binary. The Kepler mission discovered planets orbiting binary stars directly. Circumbinary planets that swing around both stars in the system. They exist. They're not common, but they exist. For EBLM J0555-57 AB, any planets in close orbits around the small star itself would need to be stable against perturbations from the larger companion. Whether such orbits exist in the habitable zone is a function of the binary separation. The survey that found it was not designed to detect planets around it specifically. Follow-up observation looking for planets in the system would be required. The planets may be there. We just haven't looked carefully enough to find them. And most known red dwarfs haven't been systematically searched for planetary companions. We know planets around red dwarfs exist in large numbers from statistical surveys, but we don't know specifically what orbits it. There's something genuinely remarkable about the fact that we can characterize a star 600 light-years away down to a fraction of a Jupiter radius. 600 light-years is not a small distance. A photon of light, traveling at the ultimate speed limit of the universe, takes 600 years to cross it. The light we're analyzing from this star left it before the printing press existed in Europe, before Columbus crossed the Atlantic. That ancient light, arriving at our detectors after a 600-year journey, contains enough information in its pattern of periodic dimming to tell us that the star it came from is smaller than the largest planet in our solar system. And we determined this not by looking at the star directly, but by watching how it periodically dims the light of its companion. By measuring tiny variations in brightness, small fractions of a percent, with the precision needed to extract geometric information from the shape of the light curve. By combining that with spectroscopic measurements of Doppler shifts to extract masses from orbital dynamics. The ingenuity required is easy to underestimate. It took generations of physicists, mathematicians, engineers, and observers to arrive at that number. 0.84. Jupiter radii. A number that describes a burning star 600 light-years away, derived from the way light dims and brightens over days. Science doesn't always announce itself with dramatic moments in large rooms. Sometimes, the most extraordinary results emerge from patient, careful measurement of things that look unremarkable until you do the analysis and understand what you're actually looking at. There's a larger frame that puts all of this in perspective. The universe builds objects across an enormous range of sizes and scales. On the large end, there are stars so enormous that their radius alone would engulf our solar system well beyond the inner planets. Stars that burn through their fuel in millions of years, explode, and leave remnants behind. Spectacular, violent, brief. On the small end, there's EBLM J0555 5-57 AB. Patient, dim, barely qualifying, and yet genuinely burning. Genuinely a star, sustaining the same nuclear process as those giants, at a tiny fraction of their scale, with a span of time ahead of it that dwarfs anything we normally think about. No explosion at the end. No dramatic death in a supernova. Just a slow, gradual dimming over hundreds of billions of years as the hydrogen is consumed. Eventually, the fuel runs out. The fusion stops. The star slowly cools toward darkness. EBLM J055 5-57 AB has barely begun. In the context of how long it will live, it is an infant. We found it right near the start of its long, quiet story. That's the thing that stays with you. When you think about a star like this, not its current smallness, not its dim, reddish glow, not the fact that it barely qualifies. What stays with you is the future. Our sun has roughly 5.5 billion years left. A long time by any human measure. But in the universe's larger accounting, 5.5 billion years is a season. EBLM J 0555-57. AB has something closer to 100 times that remaining. Or more. The stars we see when we look up at the night sky, the bright ones, the ones that formed the constellations that shaped human mythology and guided ships across oceans for centuries. Most of them will be gone long before EBLM J 0555-57A B even approaches the end of its life. The Milky Way will have changed beyond recognition. The sun will be a white dwarf, cold, and gradually cooling toward black. And this tiny, faint, Jupiter-sized star will still be burning, still fusing hydrogen, still radiating its dim red light into whatever the universe looks like then. There's something quietly significant about that. The record holder for smallest known star is also, in a very real sense, one of the candidates for longest burning. The things at the very bottom of the scale sometimes have the longest road ahead. The universe reserves its most patient fires for its smallest stars. The study of red dwarfs and objects like EBLM J0555-57AB connects directly to one of the oldest questions in science. Are we alone? That question has always been with us. It's been asked by philosophers, by theologians, by curious children looking up at night. But it's only in the last few decades that we've had the tools to begin answering it empirically. Not philosophically, not theologically, not speculatively. Empirically. By measuring actual planets, actual atmospheres, actual chemical signatures in light that has traveled light years to reach us. And the red dwarfs sit at the center of this effort in a way that nobody anticipated even 20 years ago. When the planet hunting era began in earnest, in the 1990s, with the discovery of the first exoplanet orbiting a sun-like star, the assumption was that sun-like stars were the place to look for life. They seemed familiar. They seemed like our sun. They seemed like the right environment. But as the census of exoplanets grew, an unexpected picture emerged. Planets are incredibly common around red dwarfs. The statistics suggest that virtually every red dwarf hosts at least one planet. Many host multiple, and some of those planets sit in the habitable zone. If that's true, across the full population of red dwarfs in the galaxy, the number of potentially habitable worlds is enormous. Not dozens, not thousands, potentially billions. The search for life may not begin at the nearest sun-like star. It may begin at the nearest red dwarf. And the nearest red dwarf, Proxima Centauri, is only 4.24 light-years away. The physics of what makes a star fuse hydrogen at all is worth understanding in more detail because it's the foundation of everything we've been discussing. Hydrogen fusion, at its most basic, is about forcing protons together. Protons are positively charged. Like charges, repel. Two protons pushed toward each other experience an increasingly strong electrostatic repulsion as they get closer. This repulsion is the electromagnetic force. It's one of the four fundamental forces of nature, and it's very effective at keeping protons apart. For fusion to happen, two protons have to get close enough for the strong nuclear force to take over. The strong nuclear force is vastly more powerful than electrostatics at extremely short ranges. If two protons can be forced within about 1 femtometer of each other, roughly a millionth of a billionth of a meter, the strong force binds them together and fusion occurs. The challenge is that at temperatures and pressures relevant to stellar interiors, most protons don't have enough kinetic energy to classically overcome the electrostatic barrier. If you run the calculation classically, fusion at temperatures of 10 million degrees Celsius shouldn't happen. The barrier is too high. And yet, stars fuse hydrogen. The resolution is quantum mechanics. Quantum mechanical tunneling allows particles to pass through energy barriers they classically couldn't overcome. Protons in the stellar core don't have to classically scale the electrostatic barrier. They can tunnel through it. The probability of tunneling is extremely sensitive to temperature and to the mass of the particles involved. At the temperatures and densities of stellar cores, proton-proton tunneling happens at a rate that sustains fusion and powers the star. Below the minimum stellar mass, the core temperature and density aren't sufficient for tunneling to occur at a meaningful rate. The probability drops too low. Fusion essentially stops. The object becomes a brown dwarf. EBLM J 0555-57. AB sits exactly at the edge where quantum tunneling makes fusion just barely viable. The numbers barely work. But they do work, and that makes all the difference. There's a concept in stellar physics called the main sequence lifetime, and it's worth understanding clearly because it's what we mean when we talk about how long a star lives. The main sequence is the phase of a star's life during which it's burning hydrogen in its core. The main sequence lifetime is the total time a star spends in this stable hydrogen-burning phase. It's determined by two things: how much fuel the star has and how fast it burns it. The amount of fuel is proportional to the star's mass. More massive stars have more hydrogen. The burning rate is determined by the luminosity. More luminous stars burn through their fuel faster. Now, here's the key relationship. Luminosity rises much faster than mass. If you double a star's mass, you much more than double its luminosity. The precise scaling depends on the mass range, but for stars in the range near EBLM J J0555-57 AB's mass. The luminosity scales steeply with mass. A star twice as massive might be 8 or 10 or more times as luminous. So when you scale to the very bottom of the stellar mass range, the effect is dramatic. EBLM J0555-57A. B has about 8.5% of the Sun's mass. That's about a factor of 12 less mass than the Sun. But its luminosity is roughly 2 to 3 thousandths of the Sun's. That's a factor of perhaps 400 or more less luminous. So it has about 12 times less fuel, but it burns that fuel at a rate that's hundreds of times lower. The net result is a lifespan that is measured not in billions of years, but in hundreds of billions. The math works out in favor of the small stars. It works out dramatically. The proton-proton chain, which is the fusion process operating in EBLM J0555-57 AB, comes in several variants. The simplest and most dominant in the lowest mass stars is the proton-proton-1 chain. In this variant, two protons fuse to form deuterium, a positron, and a neutrino. The deuterium then fuses with another proton to form helium-3. Then two helium-3 nuclei fuse to produce helium-4 and two protons. The net result is 4 hydrogen nuclei converted into one helium-4 nucleus with the release of energy. The energy released per reaction is fixed by the mass difference between the reactants and products via E equals mc squared. About 0.7% of the initial mass is converted to energy. That sounds tiny, and it is per reaction. But the number of reactions happening per second in a stellar core is staggering. In the Sun, roughly 3.8 times 10 to the power of 38 proton-proton reactions occur every second. In EBLMJ 0555-57A, the rate is far lower. The lower temperature and pressure mean fewer reactions per second per cubic meter of core material. The total energy output is correspondingly small. But every single reaction still converts mass to energy, still pushes outward against gravity, still sustains the balance that defines the star. The physics is identical, just at a much lower rate. The observation that EBLMJ 0555-57 AB's radius is consistent with model predictions is more significant than it might initially appear. For decades, there's been a known discrepancy in the measured radii of some low-mass stars. Many red dwarfs appear slightly larger than stellar models predict they should be. This radius inflation problem, as it's called, has been studied extensively. One likely explanation involves magnetic activity. Strongly magnetic stars may be somewhat inflated because the magnetic field inhibits convection in parts of the interior. When convection is suppressed, energy transport becomes less efficient. The outer layers have to expand slightly to maintain the energy flux. The star bloats. Magnetically active red dwarfs, which includes many of the well-studied nearby examples, tend to show the largest inflation. EBLM J0555-57. AB's measured radius agrees well with model predictions. That agreement might mean the magnetic activity in this particular star is not severe enough to cause significant inflation. Or it might mean the models are particularly good at predicting properties at this extreme low mass end. Either way, the agreement is useful. It suggests our understanding of the physics at this extreme is not dramatically wrong. But continued observations of many small stars are needed to understand the radius inflation problem fully. The EBLM survey and similar programs are building the statistical sample needed to do that. Let's talk about what we actually know about the evolution of red dwarf populations over the history of the universe. The first stars to form in the universe, shortly after the Big Bang, were made from almost pure hydrogen and helium. No carbon, no oxygen, no iron, no silicon. The universe hadn't yet produced those elements through stellar nucleosynthesis. These first stars are called population 3 stars. Based on theoretical models, population 3 stars are expected to have been very massive, perhaps hundreds or even thousands of times the Sun's mass. The reason is that heavier elements, when present, help gas clouds cool more efficiently and fragment into smaller pieces. Without those heavy elements, the gas clouds that formed the first stars may have remained more massive and less fragmented. If population 3 stars were very massive, they would have been short-lived. They burned through their fuel in millions of years, exploded as supernovae, and seeded the universe with the first heavy elements. Those heavy elements became the raw material for the next generation of stars. Stars that formed from that enriched gas are called population 2 stars. They contain some heavy elements, but less than stars forming today. Population 2 stars include some of the oldest surviving stars in the universe. Stars more than 13 billion years old. Among population 2 stars are some red dwarfs. These old red dwarfs formed from a gas composition slightly different from modern red dwarfs. Slightly less enriched in heavy elements. Their properties, their internal physics, their minimum mass, may differ very slightly from modern red dwarfs. The stars forming today, population 1, stars contain the most heavy elements of any stellar generation. Our Sun is a population 1 star, EBLM, J0555 5-57. AB is a population 1 star. It formed from interstellar gas already enriched by billions of years of stellar nucleosynthesis. Heavy elements, even in the tiny quantities found in red dwarf atmospheres, affect the star's opacity and internal physics in subtle ways. The minimum stellar mass in the early universe may have been slightly different from what we measure today. This is a research question. The answer matters for understanding how many red dwarfs formed in the early universe and how many are still burning. One of the more philosophically interesting aspects of studying stars like EBLM J 0555 -57 AB is what they imply about the far future of the cosmos. The universe today is in a period that cosmologists sometimes call the stelliferous era. The era of stars. Stars are forming, burning, and exploding throughout the galaxy. New stars are being born from molecular clouds. Old stars are shedding their outer layers. Supernovae are enriching the interstellar medium with heavy elements. The stelliferous era began with the formation of the first stars a few 100 million years after the Big Bang. It will end when the last star finally burns out. The most massive stars live and die quickly. They've been burning and exploding throughout the history of the universe. The sun-like stars live for billions of years and are burning now. Some have already burned out and become white dwarfs. The red dwarfs will outlast everything. The last star to burn in the universe will be a red dwarf. When it finally exhausts its hydrogen, the stelliferous era ends. The universe enters what physicists call the degenerate era, a long period when the remnants of dead stars slowly cool and fade, and only exotic objects like black holes provide any significant energy output. That transition from a universe lit by stars to a universe of dark remnants marks one of the most significant eras in cosmic history. And the last light before that transition comes from stars like EBLM J055 5-57 AB. The smallest stars are the last lights. The discovery of EBLM J055-57 AB in 2017 prompted astronomers to re-examine existing survey data for other stars that might be similarly extreme. The question was natural. If one star this small exists, how many more are there? Are they common? Are they rare? Are there even smaller ones we haven't found yet? The answer, based on subsequent analysis, is that the population of stars near the minimum mass threshold is real and probably numerous. They're hard to find because they're so dim. But they exist. The EBLM survey continued cataloging new low-mass eclipsing binaries. Other surveys independently identified similar systems. The picture that's emerging is of a population of very small stars near the minimum mass, not dramatically rare, but not easy to find without specifically designed surveys. Every new detection refines the statistics. Every new precise mass and radius measurement tests the stellar models. And every new system found near the boundary adds to our understanding of how nature distributes stellar masses and what the true frequency of the smallest stars actually is. This is ongoing work. The census isn't finished. It may never be finished, given the sheer number of stars in the galaxy. But it's being built, survey by survey, observation by observation. There's a connection between the smallest stars and one of the most fundamental questions in modern cosmology, which is the question of where the universe's matter actually is. Cosmologists have established that the universe contains several times more mass in dark matter than in ordinary baryonic matter, the stuff that makes up stars, gas, and planets. But even among ordinary matter, the distribution of mass is not what you might naively expect. The massive, luminous stars that dominate our view of the galaxy contribute relatively little to the total stellar mass budget. The stars we see most easily are not the stars that carry most of the mass. It's the red dwarfs. When you integrate the stellar initial mass function over all stellar masses and count up the total mass in each category, the red dwarfs win. Not because any individual red dwarf is particularly massive, but because there are so many of them. The statistical weight of hundreds of billions of small stars adds up to more mass than the relatively small number of sun-like and massive stars. This matters for understanding the galaxy's gravitational dynamics, its rotation curve, its total mass budget. Stars like EBLMJ 055 5-57a, b, the smallest and most common, are an important contributor to the galaxy's total stellar mass. Invisible to the naked eye, undetectable, without specialized instruments, and yet collectively massive in the aggregate. The galaxy is heavier than it looks, largely because of objects like this one. The process of finding new stars near the minimum mass threshold has also been transformed by the availability of data from space missions not primarily designed for that purpose. The Gaia mission, a European Space Agency satellite designed to measure the positions and motions of over 1 billion stars with extraordinary precision, has been a goldmine for stellar astronomy beyond its primary mission. Gaia measures parallaxes, the tiny shifts in a star's apparent position as Earth orbits the Sun. From these parallaxes, distances can be calculated with unprecedented precision. Knowing the distance to a star, combined with its apparent brightness, gives you its absolute luminosity. Luminosity, combined with stellar models, constrains mass. Gaia has provided distance measurements for billions of stars, including many red dwarfs that were previously too dim or too poorly characterized to place precisely on the Hertzsprung-Russell diagram. The resulting precision HR diagram reveals the structure of the main sequence in extraordinary detail, including its lower end, where the smallest stars cluster near the minimum radius. Gaia data has been used to identify candidates for follow-up observation. Stars that appear to sit near the bottom of the main sequence, with properties consistent with masses near the minimum threshold. Some of these candidates have been followed up with spectroscopy and, where possible, transit observations. The result is an expanding catalogue of very low-mass stars with well-characterized properties. EBLM J055 5-57a b was characterized before Gaia's full data releases became available. Its precise distance was known from the eclipsing binary geometry. But other similar stars are being found and characterized now, using Gaia data as a starting point. The population is being mapped. The question of how EBLM J055 5-57 AB formed is tied to the broader question of how binary star systems form in general. Binary and multiple star systems are extremely common. Estimates suggest that more than half of all stars are members of binary or multiple systems. For Sun-like and massive stars, the binary fraction is even higher. For the lowest mass red dwarfs, the binary fraction is lower, but binaries still exist. Binary systems form when a molecular cloud fragment collapses and produces two or more protostars instead of one. The details depend on the initial conditions: the rotation of the cloud, its internal turbulence, the density structure. In some cases, the cloud fragments early, producing two separate collapsing cores that evolve into two distinct stars. In other cases, a disk forms around the primary protostar, and a companion forms within the disk. For close binaries like EBLM J055 5-57ab and its companion, where the orbital period is only 7.8 days, the formation process likely involved migration. The two stars probably didn't form at their current small separation. They formed further apart and then interacted gravitationally, losing energy and migrating to a closer orbit. This process of binary migration through disk interactions or three-body encounters is an active area of research. The end state, a tight binary with a tiny cool star orbiting a larger companion every few days, is one of the configurations that the EBLM survey was specifically designed to find and characterize. And in finding EBLM J055 5-57ab, the survey found the most extreme example of its type. Understanding the smallest stars also means understanding what happens to them when they're part of binary systems with very close orbits. That 7.8-day orbital period means it orbits its companion at a very small separation. At that separation, tidal interactions between the two stars are significant. Tides from the companion raise a bulge on the star. These tidal bulges dissipate energy through friction within the star's material. This energy dissipation slows the star's rotation over time, similar to how tidal forces from the Moon have slowed Earth's rotation over billions of years. In close binary systems, both stars tend to be tidally synchronized, meaning their rotation periods match their orbital periods. If it is tidally synchronized, it rotates once per 7.8 days, faster than the Sun rotates, which takes about 25 days at the equator, but slower than an unsynchronized red dwarf might rotate. The rotation rate matters for magnetic activity. Faster rotating stars tend to be more magnetically active. If tidal synchronization has settled EBLMJ 0555-57 AB into a relatively slow rotation for a star of its type, its magnetic activity might be somewhat moderated compared to a free-spinning red dwarf of the same mass. Or the tidal interaction might drive its own dynamics. These are details that require careful observation to determine. But they illustrate that the properties of a star in a close binary aren't simply those of an isolated star of the same mass. The companion matters. The orbital dynamics matter. The history of the system matters. There's a broader context worth placing. EBLMJ 0555-57 AB in, which is the history of our understanding of what constitutes a star. For most of human history, stars were simply lights in the sky. Their physical nature was completely unknown. Ancient observers noted their positions, their brightnesses, their colors, their patterns. They tracked their motions, distinguished planets from stars by their wandering paths. They built calendars from their rising and setting times. But they had no idea what stars actually were. The realization that the sun is a star came gradually. That stars are distant suns came later. The idea that stars could come in dramatically different sizes, masses, and colors, and that these properties determine their behavior and lifetimes, is a product of 19th and 20th century science. The development of spectroscopy in the mid-1800s allowed astronomers to analyze starlight and identify chemical elements by the dark absorption lines in spectra. The discovery that stars have the same elements as the Earth and Sun revolutionized thinking. The development of stellar astrophysics in the early 20th century, with the work of researchers like Arthur Eddington, who showed that stars are powered by nuclear reactions, transformed our understanding of what stars are. The Hertzsprung-Russell diagram, developed independently by Einar Hertzsprung and Henry Norris Russell in the 1900s, organized the diversity of stars into a comprehensible picture. The existence of minimum and maximum stellar masses, grounded in physical theory, came later still. The idea that there's a floor to stellar existence, a minimum amount of material needed to make a star, is a 20th century insight. And EBLM J0555-57 AB is the observational confirmation that nature really does push all the way to that floor. That the theoretical minimum is not just a theoretical exercise. Nature actually makes stars at the minimum mass. We've now seen one. One thing that's easy to lose track of in all these numbers and physics is the sheer persistence of science as a human endeavor. The fact that we know anything precise about a star 600 light-years away is the product of centuries of cumulative work. Not one person, not one discovery, not one telescope. But generations of scientists building on each other's work, each contribution small in isolation, collectively adding up to something extraordinary. The ancient astronomers who catalogued star positions didn't know they were laying groundwork for parallax measurements 2,000 years later. The 18th century observers who built precise instruments for measuring tiny angles in the sky didn't know they were enabling the distance measurements that would eventually let us characterize stars. The 19th century spectroscopists who discovered how to read starlight didn't know they were building the tools that would eventually let us identify molecules in exoplanet atmospheres. Each generation worked with what they had, pushed as far as they could, and passed what they learned to the next. The characterization of EBLM J0555-57AB in 2017 is not the work of one team. It's the accumulated work of everyone who contributed to the physics, the instrument technology, the survey methodology, and the analytical techniques that made it possible. Science doesn't have a single author. It's a collaborative enterprise across time. And the result? The knowledge that a star barely larger than Jupiter is burning 600 light-years away is a product of that enterprise. Something no individual could have produced alone. Something that required the collective effort of centuries of curious people asking questions and building on each other's answers. The measurement of stellar masses from eclipsing binary systems is worth understanding more fully, because it's the technique that gave us EBLM J0555-57 AB's properties with confidence. When two stars orbit each other, they both move. They orbit their common center of mass. If the more massive star is much larger, the center of mass sits closer to that star, and both objects orbit around a point that's not very far from the massive star. But both move. Spectroscopy reveals this motion through the Doppler effect. As the smaller star moves toward us in its orbit, its spectral lines shift slightly toward shorter wavelengths, what we call blue shift. As it moves away, in the other half of its orbit, the lines shift toward longer wavelengths, red shift. By measuring how much the spectral lines shift and how the shift varies over time, you can determine the orbital velocity of each star. From the orbital velocities and the orbital period, you can derive the masses. Not the absolute masses, but the mass ratio and a lower limit on the individual masses. If you also know the inclination of the orbit, you can break the degeneracy and get absolute masses. For an eclipsing binary, the inclination is known. The orbit must be nearly edge-on for eclipses to happen. Edge-on means close to 90 degrees inclination. With that constraint, the masses can be determined with good precision. Combine the mass measurement with the radius measurement from the transit geometry, and you have two of the most fundamental stellar properties measured directly from observation. No stellar models required. No assumptions about the star's internal physics. Just geometry and orbital mechanics. The elegance of this technique is why eclipsing binaries have been so valuable in stellar astrophysics for over a century. The technique was developed long before modern electronics or computing. Photographic observations of variable star brightness, combined with spectroscopic measurements of Doppler shifts, were being used to measure stellar masses in the early 20th century. We've refined the technique enormously since then. The precision is far greater. The sensitivity to small companions is far better. But the fundamental physics is the same. And it's that same physics that pinned down the properties of EBLM J0555-57AB, with enough confidence to call it the smallest known star. The name EBLM J 0555-57A. B contains a lot of information if you know how to read it. EBLM, as we've established, stands for Eclipsing Binary Low Mass. The J in the designation indicates a coordinate format. The numbers that follow are the celestial coordinates. 0555 is the right ascension, roughly equivalent to longitude in the sky, expressed in hours, minutes, and seconds. -57 is the declination, roughly equivalent to latitude in the sky, in degrees. The lowercase a and b, after the coordinate, indicate components of the system. Uppercase letters like A and B typically denote stars in a multiple system. But the EBLM naming convention uses lowercase a and b specifically. The A denotes the primary star, the brighter, larger companion. The B denotes the smaller secondary, the record-breaking star we've been discussing. So the full name tells you it's an eclipsing binary with a low-mass secondary component located at right ascension, 0 hours, 55 minutes, 55 seconds, and declination -57 degrees. In the constellation Pictor, in the southern sky. Visible from the southern hemisphere, below the horizon, for most northern hemisphere observers. There's a whole universe of information packed into that alphanumeric string. Astronomers are efficient that way. The constellation Pictor, where EBLM J0555-57AB resides, is one of the fainter southern constellations. Its name means the easel in Latin, and it was introduced by the French astronomer Nicolas Louis de Lacaille in the 1750s during his catalogue of southern sky objects. Lacaille spent several years at the Cape of Good Hope, in what is now South Africa, systematically mapping and cataloguing the southern sky that European astronomers had relatively little access to. He introduced 14 new constellations, many named after scientific instruments and artistic tools. Pictor, the painter's easel, is one of them. The constellation contains no particularly bright stars. Its most notable member is the star Pictor itself, also designated Alpha Pictoris, a young star about 60 light-years away, surrounded by a debris disk. Alpha Pictoris is not EBLM J0555-57 AB's companion. They happen to lie in the same general direction of the sky as seen from Earth, but are at very different distances. The star sits about 600 light-years away, far deeper into the galaxy than Alpha Pictoris. Constellations are projections on the sky. The stars within them are at vastly different distances, often unrelated to each other physically. They just happen to lie in similar directions. The fact that it falls in Pictor is purely a matter of its sky coordinates. It tells us where to point a telescope. It doesn't tell us anything about the star's physical relationship to anything else in that region of sky. The community of astronomers studying low-mass stars and brown dwarfs has grown substantially over the past 2 decades. What was once a niche subfield has become a major focus of research. The reasons are several. The emergence of infrared survey technology made finding these objects possible. The realization that red dwarfs are enormously common made them statistically significant. The discovery that planets around red dwarfs are accessible to transit studies made them scientifically central to the search for life beyond Earth. The development of precision spectroscopy, capable of characterizing exoplanet atmospheres, made the stakes even higher. Conferences dedicated to low-mass stars and brown dwarfs attract hundreds of researchers from institutions around the world. Journals publish hundreds of papers per year, on topics related to red dwarfs and their planets. Telescope time at major facilities is being allocated to observe these systems. Space missions are being designed specifically with red dwarf science in mind. The field has, in a relatively short period, transformed from a scientific backwater to one of the most productive and exciting areas in astronomy. EBLM J 0555-57 AB is a product of this transformation. The techniques that found it, characterized it, and identified it as the smallest known star were all developed within this productive research community. And what the community found at the bottom of the stellar mass function, right at the very edge, is a star that perfectly encapsulates why this field matters. The smallest possible star. Long-lived, dim, extraordinary in its ordinariness. Let's spend a moment on what we mean by the phrase confirmed hydrogen fusion, because it's a phrase that carries real scientific weight. Not all stellar mass objects can be confirmed as genuine stars through simple observation. A brown dwarf near the minimum mass and a red dwarf near the minimum mass can have similar surface temperatures, similar colors, similar luminosities. From a distance, without precise mass measurements, they're hard to distinguish. Confirmation that an object is fusing hydrogen requires either a precise mass measurement showing it's above the threshold, or the detection of chemical evidence that fusion has occurred, or both. For EBLM J0555-57AB, the eclipsing binary geometry provided a precise mass measurement, 85 Jupiter masses, or about 8.5% of the Sun's mass. This is above the theoretical minimum mass for hydrogen fusion. The mass measurement itself is the confirmation. If the mass is reliably above the threshold, the object is a star by definition. The mass measurement from orbital mechanics is independent of any stellar model. You're measuring how fast the objects move and how long their orbit takes. From those observable quantities, you derive the masses using Kepler's laws of orbital motion and Newtonian gravity. The physics is straightforward and extremely well established. The conclusion that EBLM J0555-57A B is a genuine hydrogen-fusing star rests on one of the most solid foundations in physics: the laws of gravity, the geometry of orbital mechanics, measurements of light arriving at our detectors. No exotic assumptions, no complex modeling, just physics, applied carefully. The Hertzsprung-Russell diagram, which we've mentioned several times, is worth describing in a bit more detail because it's the organizing tool that makes the context of EBLM J0555-57 AB's discovery visually comprehensible. Imagine a graph. On the horizontal axis, from left to right, you plot temperature. But the axis runs backward from our intuitions. Hot is on the left, cool is on the right. On the vertical axis, you plot luminosity. Bright is at the top, dim is at the bottom. Now plot every star you know, each as a point on this graph. What emerges is not a scatter. It's a pattern. Most stars fall along a diagonal line that runs from the upper left, hot and bright, to the lower right, cool and dim. This is the main sequence. Stars on the main sequence are burning hydrogen in their cores. The position of a star on the main sequence is almost entirely determined by its mass. Massive stars sit in the upper left. Less massive stars sit in the lower right. The Sun is roughly in the middle. Now, trace the main sequence from the Sun's position downward and to the right. As you move lower right, the stars get less massive, cooler, and dimmer. Red dwarfs span a wide range of the lower right. At the very bottom, at the extreme lower right corner of the main sequence, sits EBLM J0555-57 AB. Below its position on the diagram, there is no more main sequence. There are only brown dwarfs and planets, which don't fuse hydrogen and don't belong on the main sequence at all. It sits at the terminus, the end of the line. Beyond it, the concept of the stellar main sequence simply stops. One practical consequence of stars being this small and dim is what it means for the search for planets around them. Detecting a planet around a star using the transit method requires measuring the fraction of starlight blocked when the planet passes in front of the star. That fraction is the ratio of the planet's disk area to the star's disk area. For a planet the size of Earth, transiting our Sun, the blocked fraction is about 84 parts per million. A very small signal. For a planet the size of Earth, transiting a star, the size of EBLM J0555-57 AB, the calculation is different. The star's disk is much smaller. The fraction blocked by an Earth-sized planet is much larger, perhaps a few percent. That's a signal orders of magnitude larger and easier to detect. An Earth-sized planet transiting a star. This small would produce a transit signal similar to what a Jupiter-sized planet produces when it transits our Sun. Jupiter transits produce signals around 1%. We can detect 1% signals easily with modern equipment. This means that Earth-sized planets in the habitable zones of the smallest stars are actually within reach of transit detection. For Sun-like stars, Earth-sized planets in the habitable zone produce signals too small to detect reliably with most current instruments. The smallest stars level the playing field. They make Earth-sized habitable zone planets findable. This is one of the most important practical implications of the existence of very small stars. The smaller the star, the more accessible its planets are to study. EBLM J0555-57 AB and its cousins are not just scientifically interesting as the smallest stars. They're among the best possible targets for finding and characterizing potentially habitable worlds. The relationship between stellar flaring and habitability is nuanced enough that it deserves a deeper look. The concern about flaring isn't just that ultraviolet radiation can damage DNA. It's that flaring contributes to atmospheric erosion over geological time through several mechanisms. Ultraviolet radiation can photodissociate atmospheric molecules. Water vapor, for example, can be broken by ultraviolet photons into hydrogen and oxygen. Hydrogen, being light, can escape to space from a planet with low enough gravity. Over billions of years, this photodissociation can remove a planet's water inventory. Stellar winds, the streams of charged particles flowing outward from a star, can also erode atmospheres. Red dwarfs have more intense stellar winds relative to their luminosity than Sun-like stars, partly because of their higher magnetic activity. Planets without strong magnetic fields of their own are more vulnerable to this kind of atmospheric stripping. Flares amplify both effects. During a flare, ultraviolet output spikes. Energetic particles flood the space around the star. A planet in the habitable zone is hit with a burst of everything that damages and removes atmosphere. Over hundreds of millions of flares across a stellar lifetime, the cumulative effect could be significant. Whether planets around the smallest red dwarfs can retain enough atmosphere to remain habitable depends on a competition between atmospheric loss and replenishment. Geological processes, volcanic outgassing, impacts, can replenish atmosphere. If replenishment rates exceed loss rates, a planet can maintain its atmosphere over geological time. If not, the planet gradually loses its volatile inventory. The outcome depends on the planet's geology, its magnetic field, its distance from the star's flaring frequency and intensity, and probably several other factors we haven't fully identified yet. This is why the habitability question for red dwarf planets isn't settled. The physics allows for planets that retain their atmospheres. The physics also allows for planets that don't. The observations needed to distinguish these cases are only now becoming possible with instruments like the James Webb Space Telescope. The concept of the habitable zone itself deserves a bit more examination because it's sometimes misunderstood. The habitable zone is not where life definitely exists. It's not even where life is necessarily likely. It's the region around a star where liquid water could theoretically exist on a rocky planet's surface, given certain assumptions about atmospheric composition and pressure. Those assumptions matter. Earth sits in the Sun's habitable zone. But if Earth had a different atmosphere, different surface pressure, different albedo, the same distance from the Sun might be too hot or too cold for liquid water. Venus is just inside the Sun's inner habitable zone boundary. With Earth's atmosphere, Venus might have liquid water. With Venus's actual atmosphere, it has surface temperatures of around 460 degrees Celsius or about 860 degrees Fahrenheit. The habitable zone is a useful concept for organizing our thinking and prioritizing targets for observation. But it's a starting point, not a conclusion. A planet in the habitable zone requires further study to determine whether it actually has the conditions for liquid water. For red dwarf planets, the habitable zone calculation also has to account for factors specific to those systems. The tidal locking that's likely for close-in planets changes the thermal structure of the atmosphere and the distribution of temperature across the surface. A tidally locked planet has a very different temperature map than an Earth-like, rapidly rotating planet. Whether liquid water can persist on a tidally locked planet in the habitable zone depends on atmospheric circulation, which in turn depends on the amount and composition of the atmosphere. These are computational problems that researchers model carefully. And the models have improved dramatically in the last decade as computing power has grown and as the specific questions have come into focus. We now have genuinely sophisticated climate models for tidally locked planets around red dwarfs. Some of those models suggest that, under the right conditions, liquid water can persist in temperate regions. Others suggest it cannot. The observational data needed to test the models definitively are what the current generation of instruments is working to provide. The next time you look up at a clear night sky, the red dwarfs are there. You just can't see them, even the nearest ones. Even Proxima Centauri, our closest stellar neighbor, is invisible to the naked eye from Earth. You need a telescope to find it. Stars like EBLM J0555-57AB, 600 light-years away, and 2 or 3 thousandths the Sun's luminosity, are completely undetectable without specialized equipment. They don't announce themselves. They don't put on a show. They sit quietly in the darkness between the bright stars, carrying the majority of the galaxy's stellar mass in objects we can barely detect. The universe is mostly made of things that are hard to see. Dark matter, which we detect only through its gravitational influence. Diffuse gas between galaxies. Black holes that reveal themselves only when material falls into them. And red dwarf stars. Hundreds of billions of them. The most common star in the galaxy. Among the least celebrated. We built our picture of the cosmos around the bright exceptions. And then, slowly, with better instruments and more careful surveys, we started finding what was actually there. The smallest star ever found is smaller than the largest planet in our solar system. It barely qualifies as a star. And it may burn for longer than anything else in the universe. The universe doesn't waste its quiet fires. If you found this journey into the extreme small end of the stellar scale as absorbing as we do, a like or a subscribe helps these explorations reach the people who want to find them. The universe is built from extremes on both ends, and the small end of the scale turns out to be every bit as extraordinary as the large end. Just quieter about it. Good night.